This will be the data.
Oh,
I'll show you. OK. So, hi, my name is Paul. I'm here to talk to you about timing attacks. Before we get started, the references for my slides are all on the speaker notes for the slides themselves, and the slides will be on GitHub right after the talk. So, who am I? I'm a security engineer at Nebula. We built the cloud computing hardware. I'm also security response for a number of large open source projects you've probably heard of. I like doing developer outreach. I like teaching security. Mostly I work in Python. I like building distributed systems. And I like taking theoretical vulnerabilities and making them practical. So we're going to talk a little bit about the Internet of Things. There are lots of ways to attack them. You own the hardware. You can take it apart. You can read the memory. You can do fuzzing. You can exploit logic errors. All sorts of fun things. Often they're running badly secured embedded systems. We're not going to talk about how to use those kinds of attacks today. Instead, what we're going to do is we're going to demo using a string comparison timing attack on an embedded piece of hardware. You want to come do some video now? Yeah. You're on. OK. So what we have here is the Philips Hue light controller for which is a Zigbee-based colored lighting system. It's put out mostly sold through the Apple Store in the US. This base station is connected via a hardwire to what I have here, which is an external network card on my laptop. I'm using the external network card because it supports hardware timestamps, but you can do this without hardware that supports timestamps. It just will take you longer. So can you look at this screen? If we can't do that, all right. So what I'm going to do here is I'm going to start the demo. The reason I'm starting the demo at the very beginning of the talk is because the demo has a while to fail, and also I expect this is going to take most of my talk for the demo to actually succeed in breaking into the device. What the code on my screen is doing right now, which you absolutely can't see, is it is repeatedly making API requests to the device. Rather than brute forcing it, though, what it's doing is it's trying every single possible first character, and I'll show you in a minute how that turns into an attack that we can end up doing in much faster than the time that it would take to actually brute force the device. So, what is a timing attack? At a most basic level, asking the computer to do anything takes a certain amount of time, a measurable amount of time. A timing attack exploits this. It looks for differences in similar operations and allows us to figure out information about the system. So, moving on. This is a fairly typical login function for a website. I know there are some issues with it, but the main one we want to highlight here is, let's look at how it goes through here. You start, you are accepting a login from a user, so you want to find out if they're in your database and if they have the correct password. So you pull out this, you get the password hash from the user, you go look it up in the database, and then you say, if you've got a stored hash, then you check it. If you don't, you just return right away because the user isn't in your database. If you do have the stored hash, well, then you hash the password itself yourself the way you expect it to be in the database, and then you compare those two, and then you allow the user in if the password's correct. This function has a timing vulnerability. The obvious one here is that if the user isn't in the database, it returns very quickly. If I make a bunch of requests trying to log in as a username, if I look at the ones that return more quickly, I'll be able to tell which users are in your database. That's one kind of timing attack. It's also not the kind we're talking about today. The other timing attack this has is down where it tests to see whether the hash that it computed is the same as the stored hash. That is using an equality. It's just doing a basic string comparison, which takes a fairly small amount of time, but that's the same kind of vulnerability we're exploiting in the device here on stage. So other kinds of timing attacks. So we've got the user enumeration, like I just pointed out. We also have blind SQL injection. That can be used. Timing can be used to do that. You've got CPU cache timing attacks. You've got Lucky 13. Lots of things that aren't what we're doing today. String comparison timing attacks, however, are generally much more difficult to exploit than the previously mentioned vulnerabilities. Usually people will tell you they're not exploitable at all. That's why I have the demo here. So this is the actual this is an excerpt from the actual string comparison function that device is running. This is very typical. Most implementations have something similar to this. We don't need looking at the demo here until it does something interesting, which will be in about half an hour. So if you want to turn off the camera, it's cool. So the way this works is we take the first 2 bytes of the strings that we're going to compare. We subtract them from each other, and we see whether there's a difference. If there's not a difference, then we keep going. If there is a difference, we stop and we return. The key takeaway here, and so we keep doing this until we either find a difference or we get to the end of the string. The key thing here is that we have the same kind of behavior where we behave differently if a character is correct or if it's incorrect. So let's walk through this with an example. So I have a string here that I want to figure out. And so what I'm going to do is I'm going to go and make a bunch of requests to my device with a bunch of hypothesis strings. In this case, I know the string starts with A, B, C, or D, and so I make a bunch of requests with each one. Then I go and I look at the time that it took to make each request, and I look to see which one took just a little tiny bit longer. That little tiny bit longer means that you're going from just comparing the first character and saying, oh, these are different, and stopping, to comparing the first character and then comparing the second character. We did a little tiny bit more work. It's not a lot of work, but it's a little bit. So I look and see which one took longer. I say, OK, I'm going to make that one my guess. Now, so I guess that character every time that I make another guess. Now I'm going to do the same thing for the second character. I do that. I make 10,000 requests or something for each of these. And I come up with the fact that B is taking a little longer. I can keep doing this for C and so on. And we can eventually figure out the answer without trying every single combination. This gives us a massive speed up, especially for longer authentication strings. The time to do a brute force is the size of the character set, so the potential characters you can be using in your password, raised to the power of the number of characters you have. With a timing attack, it's only the number of characters times the length of the string times another constant. And that constant is how many tries you need to actually be able to detect that this one is taking a little longer than that one. So I think I've explained the basics of how string comparison timing attacks work. They're interesting to me because it's a lot like going in the front door. You're not relying on some underlying specific vulnerability in the system other than that they used basic good practices. They don't require code to have made obvious mistakes. Most people don't think that you can even do them at all. And so most people don't write code that defends against them. The downside to doing this kind of thing, especially over the network, is it takes a lot of network traffic. It's really noisy. If someone looks at their logs, they'll notice what you're up to. It's very time-consuming. I'm hoping to have the demo complete here while I'm on stage, but there's a chance that it will just take longer than we have right now. And these attacks work best on slow devices. The Internet of Things, embedded microprocessors are easier to attack with this kind of thing than a really fast machine. The other problem with them is they're very susceptible to network noise and device contention. If you're doing other things on devices, your attack's going to take a lot longer. Fortunately, we have solutions to these things. So let's take a little bit of a diversion and talk about time. Let's look at some examples of sort of what the kinds of numbers we're working with here are. So the internet from San Francisco to New York takes about 70 milliseconds. Accessing data on a spinning disk takes about 13 milliseconds. Time to get to RAM takes about 83 nanoseconds. Access to the L1 cache on a CPU takes about 1 nanosecond. And one CPU cycle takes about a third of a nanosecond. We move on, the speed of light in a network cable, a meter in 5 nanoseconds, 20 meters in one microsecond. So nanoseconds are a really small number. I know this sounds obvious, but you have to really think about the normal numbers you're thinking about in computers when you start saying, thinking about how much the difference that we're measuring here is. So for a string comparison, we're trying to measure a difference that's probably in the multiple nanoseconds, probably sub 10 nanoseconds. But that's on a modern, let the plane go by. But those numbers are all on a modern 3 gigahertz server class machine. That's not what we're attacking here today. So this is a little bit slower. This is the Philips Hue light bulb system. It's got 120 megahertz STM32 processor in it. It's got a wired network connection, which is attached to my demo machine. And then it uses Zigbee to control a wireless set of lights for your house. These are fun because you can control the color. You can control them from your phone. They're very gadgety. It's also a pretty good example for actually conducting this attack. The comparison is still going to take nanoseconds on this device, but it's going to take kind of a lot of them. So let's talk about network timing precision. Once we've decided that we have a device we're going to attack that has a string comparison in it, and the string comparison is probably slow, what do we need to do to optimize so that we can actually conduct this attack? If you want timing measurements good to the millisecond level, you can use the built-in kernel timestamping in TCP dump. Just plug it into your laptop's network card, and you're fine. The kernel's pretty good at this. It'll give you numbers that go down to the microsecond, but those numbers are pretty wonky. They don't actually give you very much data. The effects we're looking for are quite a bit smaller than the microsecond level, so we have to take some extra steps. Other things that can get in the way when you plug a network device into your computer and want to make careful timing measurements on it. Graphics drivers are very noisy. Background networking, USB devices, power-saving audio devices. When you first start doing this kind of attack, disable all of those things. You want to start making this as favorable to yourself as possible, and then once you've figured out how to do your attack, you've figured out that your device is actually vulnerable, then is the time that you can turn these back on and make it more practical. As you add noise, the amount of samples you have to take goes up, and your practical time to conduct the attack goes up. But since we're demoing this on stage, I've done everything possible to make it go as quickly as possible. So software timestamps are noisy. Let's use the hardware. Turns out this is easier than when I started working on this about a year and a half ago. Linux support for hardware timestamps is finally working out of the box in recent distributions. Most of the results we're going to keep talking about here are obtainable without hardware support, but you have to take many more samples. They're going to take a lot longer. When you're choosing a network card to use for this purpose, try to find one with hardware support for timing, which means usually that it's got IEEE 1588 support. That's Precision Time Protocol. That is used to gather packets, and sometimes it can only do hardware timestamps in one direction. So read the fine print on your hardware. So this is what we're actually using here today. Since my laptop hardware doesn't have support for hardware timestamps, I went looking for a higher quality source. What I ended up with was the Intel i350 network card. This is a server-grade card. It's pretty common in server-grade hardware. Usually you'll see it as the 1 gig NIC on higher-end server boards. When they decided, OK, yeah, we're going to go a step above the Broadcom for the 1 gig NIC. This, according to the data sheet, supports hardware timestamping with an 8 nanosecond resolution. That's a lot better than we get out of the kernel. So then it's connected into my laptop. My laptop doesn't have a PCI Express bus, so it's plugged in via a Express card to PCI Express adapter. That, for these purposes, looks to the computer like the card is just plugged into it. It's not really an issue for the timing properties or anything like that. It allows us to do this with very low latency. We couldn't do this, for example, with a USB network card. So how is the demo going? So looking at the demo here, it looks like it's guessed it's currently 2 characters into the attack and is continuing to collect data. It just decided that it had gathered enough data to break the second character in the 10-digit password that we're breaking here. So let's see. Let's talk about how we're actually doing this now. So the data collection process is pretty straightforward. We generate repeated traffic that's trying a whole bunch of what would be valid logins, and it takes the prefix that we know. In this case, we've cracked the first 2 numbers, which are 70 on the API key that we're breaking. And then we generate, then the next character is the character we're testing. And so we evenly generate a distribution of all of the other possible characters. In this case, we're just using the octal character set, so the character that comes after is 0 through 7. And then after that, we're actually doing a hybrid attack, where after that, we are brute forcing all the remaining characters. And we're doing the timing attack if we can, but this allows us to also do the brute force at the same time. So if we get lucky with the brute force, we can obviously use that, and it doesn't hurt us to do the brute force while we're also doing the timing attack. As we get more characters in the timing attack, the brute force gets more likely, and by the time we get down to 5 or 4 characters, the brute force will probably kick in and kick us over the edge. But the first characters we're doing are the ones that are really making this possible to do on stage, as opposed to over the course of however long it takes you to brute force this thing. So our basic workflow here is we generate the repeated traffic. We take a TCP dump of the packets using the correct flags to get the hardware timestamp support. Then we analyze the data, and then we feed that back into the code that's generating the repeated traffic. Let's see. So making things work here. You're going to need at least libpcap 1.5, TCP dump 4.6, and a recent kernel. You'll probably have to compile libpcap and TCP dump yourself to get the hardware support. I don't think, maybe it's in the latest Ubuntu release. At least these things are now released versions. When I started doing this, the patches were just in GitHub, and you had to apply them yourself. In theory, this might work on OS X. I haven't tried it, but let me know if it does work for you. Let's see. So now that we've captured these packets, what do we do with them? Scapy is sort of the canonical easy tool for tearing apart PCAPs, in Python at least. It doesn't support these files with the newer style timestamp. And while I spent some time working on it, it didn't want to just easily do that. So I went looking around at other options. Wireshark does support these nanosecond level timestamps. Wireshark is useful for human analysis. It's not so good for computer analysis. So I went ahead, and the latest code uses a fork of dpacket. It's in my GitHub repo. You'll need to use that version, the version that's in my GitHub repo, if you want to run this analysis code yourself. The main thing was just changing it so it worked properly with these nanosecond as opposed to microsecond level timestamps. One of the other problems with nanosecond level timestamps, here actually, while we've got this up, let's look at what's going on here. So what you can see here is that the code is currently in the data collection phase. Every 3,000 or so every 3,000 requests or so, it will stop, which it should do in just a second here, and it will analyze the results and give us some statistics about what's going on with our current guesses. There we go. So now it started the analysis there, and what you see here at the top is the p-values for the guesses that it's the data that is collected. And then here are our analysis results, which say that the 707 is the best guess that we have there. And so it changes the guess to that, and it tells us how long it took us to guess that, to use the timing attack to get that character. In this case, we can see that it took us 415 seconds to produce the statistics that made the program pretty sure that that was the next correct character. And I have the answer here because I'm cheating. Looking at it in the answer, the program is doing the right thing. It did choose the next correct character. Can we get the slides back? Slides? OK, so we can keep watching the analysis there on the side. That's entertaining as it keeps chunking through the characters one at a time. Other issues with working with nanoseconds in your code. If you convert a pure nanosecond timestamp to a float, you lose a whole bunch of the precision you just worked so hard to get. So what we do instead is we treat them as an integer, and we subtract a large offset so we don't have to deal with rounding and other errors associated with that. It just generally makes the code cleaner and easier, and you have fewer problems when you do that. So the Hue API. So this is the API that the attack code is talking to on the device there. It's very basic. You send a GET request to this URL, and if it's correct, it gives you a bunch of information. If it's not correct, it gives you a little tiny error message, and you can tell the difference very easily. That obviously only happens once you know the full token, though, which is the point of our attack. It's a basic RESTful API. It's really pretty dumb. It always returns HTTP status 200, even if there's an error. And the user token is the only required auth. You don't need a username. There are no sessions. It's just the token. As I said before, the device is 120 megahertz, and it's running the network stack on that. So it can handle about 60 requests per second. If we look at what we're getting right now, it looks like on average 59.5 requests per second. Depending on, you can actually see that number change pretty drastically depending on the temperature. When you heat it up, it starts doing wonky things and gets less repeatable. So other oddities with this device. It's running free RTOS 6.05. This is something which gives you enough of an operating system that people who aren't embedded developers can develop for these small, slow, inexpensive microcontrollers. I think that microcontroller costs $4 when you buy them in bulk. The network stack is not very good. The SSD implementation, the SSDP implementation, which is a device discovery protocol, ignores most of the parameters you pass to it other than the one or two that they needed to implement for their software. The HTTP stack ignores most of the request and response headers. And sometimes it just gets the Ethernet frame check sequence wrong. I don't know why. It's also pretty noisy. It broadcasts a lot of different things. It looks for open DNS. It's generally trying to get out to talk to the internet as well as your local network. I've shut some of that stuff up by telling it that my computer is the DNS server, and whenever it looks up a host name, telling it that my computer is that host name, so it just gets a connection close, and then it doesn't constantly retry trying to access these external services it's not going to get. So let's talk about the statistics we're doing here. I know they're terrible, but you're not going to have to sit through too many of them. So first of all, let's talk about what the null hypothesis is. Since we're using a statistical method, we need to know what the null hypothesis is. So with the methods that we're using, we have two samples, and we want to compare them and see if they come from the same distribution or a different distribution. The null hypothesis is us saying, I believe that these samples come from the same distribution. If we fail to reject the null hypothesis, we can't say anything useful about the samples other than that we have failed to reject the null hypothesis. We haven't said these samples come from the same distribution. We've just said, I don't know that they come from different distributions. If, however, the p-value from the test is small enough that we are comfortable with accepting it, that means we can reject the null hypothesis and we can say definitively, I know these two samples come from different distributions. And so in the case of our attack here, we have a correct distribution and an incorrect distribution. And we're comparing samples from each of those, and the one that sticks out, the one that isn't the same, is the one that we want to latch onto and what the test can help us identify. If you look at the statistics with your eyes, you really can't see which one is taking longer. You really have to use the statistics. Okay, so more stats. Why can't we use the t-test? The t-test is the first thing you're taught in stats class. It's great. It's useful in a lot of cases. It only applies to normal data, data that looks like this. Your network data here is absolutely not normal. It's very strange, very bumpy, all kinds of strange things going on. So the test we're going to use here is called the Kolmogorov-Smirnov test. The way it works is you take your two distributions, you sort them, you sort each of them, and then you plot them on top of each other. And then you take the largest difference between those two plots, and you do a little bit of math to that value. But that's what you use to decide whether the distributions are the same or different, based on how far apart they are at the widest value. So data prep. When you look at your data, which I will see if we can do this. When you look at your data, you want to pick the cleanest part of your samples that you can. You don't want to clip data arbitrarily. If you do that, you're going to end up contaminating your statistics. But if you can find a oh, this is not going to work. Sorry, I can't show you the pictures. If you can find a but if you can find a clean part of the data that is less noisy than the rest of it, you can actually make your stats work much better. We're going to move on from this because I'm running low on time. The code's in my GitHub repo. We'll talk about that later. How are we doing on the attack here? So it looks like we are four characters into the attack, and we're working on the 5th character. I'm going to let that keep running, but in the meantime, let me see if I can show you what I mean about the data. So this would be a fairly typical distribution of data for your unfiltered cut. These are samples. As you can see, these are 8 different samples. They all tend to clump together. None of them stands out as being particularly faster or slower than the others. And you have this striation of the distributions here. You've got a lot of random stuff up here, which is just noise. But then you've got this stuff that takes just a little bit longer. So what we do when we're doing the attack is we filter just this piece here, the accurate bit. And we only use those data points. And that lets us do the stats much more effectively. So this is what it looks like when you filter down to just those values. There are 2 bands here, but we don't want to try to filter any more narrowly than this, because we're going to start contaminating the data if we do that, and we'll be choosing an arbitrary value for the that will clip the data, and we'll lose the parameters that we need. So let's go back to the attack. The attack might still finish while I'm talking here. So back to the slides. There we go. So some tips and tricks for how to do this. We're going to blast through these very quickly because I'm running low on time. So when you make an HTTP request, this device closes the socket after you make one request. If you can keep it open, it saves you on network traffic. Configure your network card parameters properly. Turn on the hardware timestamps. Turn off the queues. Use nanosecond timestamps. Turn off the hardware Ethernet offloads, because those tend to interfere with the timestamping. Make everything quiet, both on your laptop and on both on your attack device, and if you can, on the device which is being attacked. If you have a busy web server you're attacking, you could use slow LoRa's to exclude everyone but yourself. Don't run extra stuff on your attack machine. Profile your victim. Look at when it's busy. Don't attack then. You can do these attacks over the course of months if you need to, 1 character at a time. And it's perfectly valid to do 1 character and then wait until tomorrow when it's not busy again and do the next character. If you're attacking an embedded device like this, start the device running and do a warm-up before you actually start collecting data. The data parameters change pretty rapidly over the first couple of minutes, and that can often mean that your first statistical comparison takes a lot longer to determine because the actual distribution changed as you were collecting the data. If the distribution stays the same, that's your best bet for getting the stats to work. Find the simplest request possible. Don't send more network traffic than you need to in order to carry out the attack. If you can do this with an options header as opposed to with a full-blown make the device send me a whole page, you'll do much better. It will be quieter. If you're going to branch out and look at other statistical tests, make very certain that something in the chain is not assuming your data is normal. If it is, this will absolutely not work. Gather data on all your hypotheses concurrently. You can't say, I'm going to make a bunch of requests for 0, and then I'm going to make a bunch of requests for 1, and then 2, and then hope to compare them. The properties of the device vary over time in ways that you can't control, and so you have to make a request for 0, then 1, then 0, then, and interleave your requests. Otherwise, the stats just absolutely don't work. Looks like we've brute force. We've gotten another character there. Is that? Yeah, that is correct character. Let it keep running. So randomize the request order. Don't always cycle through your list in order. If you do that, you'll end up with weird anomalies based on mutual clocks. You'll end up in cycles where one character always gets a different kind of answer than the others. Don't overwhelm the device. If you do the device, you'll end up with worse data than if you slowed down a little bit. Don't forget that you can also brute force the token while you're doing this attack. There's no reason you shouldn't be brute forcing and timing attacking at the same time, because one may work before the other does. Some code short circuits if the strings aren't the same length. This implementation does. A lot of them don't. But make sure that you're sending an attack string that's the same length as the token you're trying to validate. Don't send just a short attack string and hope to get it. Try both fast and noisy and slow and quiet. Sometimes going slowly actually gets you better data. It depends on the device. Don't be fooled by your own data. Doing this attack will teach you more than anything else in the whole world how much people find patterns when there are none. You will do your science, you'll take a bunch of data, you'll try a bunch of different things to make the stats work, you'll get the right answer and you go, yes, I figured it out. And you'll only have figured it out, you'll have overfitted to your particular sample of the data. And that won't get you anywhere. What you have to do is propose a hypothesis and then figure it out whether it works on your data, and then gather more data and try it on the new data. It's only valid if it works on a lot of data, not just the data you happen to have. This is a really useful quote. If you try hard enough, eventually statistically significant findings will emerge from any reasonably complicated data set. This is especially true if you just try a bunch of statistical methods until you find something that gives you the answer you want. When results are analyzed in many ways without a plan, the results cannot be interpreted. At best, you have to treat the findings as a hypothesis to be tested for future studies with new data. So it doesn't look like we got quite all the way through the attack. I expect it'll work in the next 5 or 10 minutes. But do I have any questions here in the last few minutes? All right, then. Well, come talk to me afterwards. I'd like to help you get started doing this kind of attack, too. It's really fun. It's very interesting. Yeah, thank you very much.
Muchas gracias, Paul.
All right, it just worked. So in a second, this should come on.
Okay.
Is that still on? Can you show them what it looks like when it works? So there you go, a timing attack. I attacked 10 digits in just under an hour. So that's pretty cool. Thanks a lot, guys.
Thank you, Paul.